Okay, welcome back. In this video we're going to cover section 1.12b, so dilations of functions. This builds heavily off of the previous section, 1.12a, so I recommend watching that one first if you haven't already done so. But with that being said, we're just going to pick up where we left off with the transformations we were already presented, but now we're going to introduce vertical and horizontal dilations. So first we have to be able to identify where a vertical or horizontal dilation occurs. So going to look at this first. So for a vertical dilation, this is found when some number is being multiplied in front of our function like this. So if we see something like 3x squared, negative 2x, 5 absolute value of x, any of these things where we have some number being multiplied in front of a parent function, this is going to be a vertical dilation, and these can also be fractions as well. So if we have a 1/2 x squared or negative 0.3 x squared, any of these are vertical dilations, so by these numbers. Well, particularly, anything is a vertical dilation, this number is a vertical dilation by the absolute value of whatever a is. So, in this case, where we have positive numbers, this 3, 5, and 1/2, these are all vertical dilations by 3, 5, and 1/2 respectively. However, this negative 2 and this negative 0.3, these are also vertical dilations by 2, because the absolute value of negative 2 is 2, and by 0.3, because the absolute value of negative 0.3 is 0.3. So, regardless of the sign of a, it's always a vertical dilation by the absolute value of a. So we can take away the sign. However, if a is negative, so if a is less than 0, then it is also a vertical reflection, also known as a reflection over the x-axis. So, for these 3, 3, 5, and 1/2, there's no vertical reflection because these aren't negative numbers. However, for negative 2 and negative 0.3, these are vertical reflections along with vertical dilations. So there's two transformations happening for both of these functions right here. But now that we're able to identify vertical dilations, let's talk about what that does to all of our points. So first, let's look at number 1. So for number 1, we have this 3 out in front of our function, and then we have this minus 5. So first we have a vertical dilation by 3, and remember we have to do our transformations from left to right. So we have a vertical dilation by 3, and then this minus 5 out here will move our function down 5 units. So with a vertical dilation of 3, basically what we do with all of our y-coordinates is we multiply our y-coordinates by the absolute value of whatever this number is. So this is a 3, so all of our y-coordinates are going to get multiplied by 3. Well, the y-coordinate of this point is 0, so it stays where it is because 0 times 3 is still 0. But the y-coordinate of negative 2 comma 2, the y-coordinate is 2, so now multiplying that by 3 is going to make it 6. So this becomes 1, 2, 3, 4, 5, 6 right here. So that's the new point. And let me note the other point. It stayed where it was. This one, same thing. We have the y-coordinate of 2, and this becomes 6, so 3, 4, 5, 6. And then this point down here has a y-coordinate of 0, so it stays where it is, because Again, 0 times 3 is 0. And now, so our function so far with the dilation will look like this. But now we still have to move our function down 5 units. So all of our points that we've made so far, we have to move them down now. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. So our new function, g of x, will look like this. And there we go. So now our function has both of these transformations. Now let's look at number 2, because this has what's called a horizontal dilation. So similar to the vertical dilation, this one for horizontal dilations is some number multiplied times x, but inside these parentheses. So I'm going to abbreviate this as HD for horizontal dilation. However, we're going to say that this is a horizontal dilation by 1 over the absolute value of b. So compare these. Vertical dilations, we can read off whatever this number is and put absolute value bars around it, and it's just vertical dilation by whatever that number is. For horizontal dilations, we have to do by 1 over b. So that's a very key difference there. So for example, if I have, using the examples from above, oh well, I guess I can't really do that because those are all vertical dilations. But if I do 3x squared like that, now this is right here a horizontal dilation by 1 over absolute value of 3, which is really just 1 over 3. So horizontal dilations, you just have to remember to put 1 over the absolute value of whatever this value is. And so similarly, if we have something like the absolute value of 1/2 x, well, now this is going to be a horizontal dilation by 1 over 1/2. I'm not putting the absolute value bars because it's already positive. However, 1 over 1/2 is equal to 2. So this would be a horizontal dilation by 2. And so with that in mind, if we, and we also, of course, can have this negative. So if b is negative, so if b is less than 0, then it is also a horizontal reflection, aka a reflection, if we're going to use our Algebra 2 terminology, if you're my student from last year, over the y-axis. So, now that we know that, let's look back at number 2. So for number 2, we now have this f of 1/2 x. This right here is our horizontal dilation by 2. And so what that means is we are going to multiply all of the x coordinates by a factor of 2. So for this point right here, the x coordinate is -4. If we multiply the x coordinate by -4, it becomes -8. So this coordinate is going to go right there. This one, the x coordinate is -2. So multiplying that by 2 is going to move it over here. This coordinate the x-coordinate is 0. So it stays the same because 0 times 2 is still 0. And then this one, the x-coordinate is positive 2. Multiplying it by 2 is going to move it to positive 4. And so I'm going to tilt my paper so I can draw this correctly. But there we go. Since that was the only transformation done, this is what our function now looks like. So notice that when this number is less than 1, it gets stretched, which is kind of counterintuitive to what happens when we have a vertical dilation. So just keep that in mind, and that's why it's important to do 1 over absolute value of whatever this number is. So what about number 3? Well, we have a negative out front. Implied this is a 1, so we're not dilating it any. However, we do have a vertical reflection. So first, let's do that. So these coordinates right here are going to stay the same because if we reflect it over the x-axis, they're not going to move at all because they're already on the x-axis. However, this point right here, since its y-coordinate is negative 2, the new y-coordinate is going to be a positive 2. And similarly for this point over here, the y-coordinate is positive 3, so the new y-coordinate is going to be negative 3. And so, if I just make a dotted graph of that so that we can clearly see what the first transformation was, now we have to combine that with our knowledge from 12a with minus 2. Minus 2 is going to move our function to the right 2 units. So now we have to take particularly these 4 coordinates. I think they're probably the most important ones because they give us the identifying features of our function here. We just have to move them all over right 2 now. So this one's going to go 1, 2. This one's going to go 1, 2, 1, 2, and 1, 2. And now connecting that, our new function for g is going to look like this. And so those are our transformations. What about number 4? We have 1/2 f of x. Well, since this number is out in front, this is going to correspond to a vertical dilation. And remember, it's just a vertical dilation is just the absolute value of whatever this number is, which is still 1/2. And so, a vertical dilation by 1/2 means that we're going to multiply all of the y-coordinates by 1/2. So, again, these two are going to stay the same because the y-coordinate is already on the x-axis, so it's not going to change at all because 0 times 1/2 is still 0. However, this coordinate right here, it's negative 2, but now since we're cutting it in half, it's going to become negative 1. It's going to go right there. And this coordinate right here is 3, but since we're multiplying it by 1/2, it's going to become 1.5, or 3 over 2, just right there. And since that was the only transformation performed, we can now connect our function, and it'll look like this. So it's going to flatten out. So that's an observation to make, is that when you have a vertical dilation by a number less than 1, it flattens out, it shrinks it. For number 5, we have f of negative x minus 4. So this negative is being applied on the inside of these parentheses, which means that it's going to correspond to a horizontal dilation. But because it's an implied negative 1 there, it's actually not being dilated at all. The only thing that's happening is it's being reflected. So we have a horizontal reflection. So a horizontal reflection means that we're going to reflect all of the x coordinates over the y-axis. So starting with this point right here, it has an x coordinate of negative 2. So reflecting over the y-axis is going to move it right there. This point has a an x coordinate of positive 1. So the x coordinate is now going to be negative 1. This point right here has an x coordinate of positive 2. It's now going to have an x coordinate of negative 2. and this point right here has an x-coordinate of 5, and now it's going to have an x-coordinate of -5. So, connecting these with a dotted line so we can at least see that transformation. So we have a reflection over the y-axis, or aka a horizontal reflection. Now we have to move all of these points down 4. So taking this point, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Now we can connect these 4 points, and we get a graph that looks like this. And for number 6, we actually want to keep it in this factored form. It may be tempting to write it as f of 2x plus 2, but we don't want to do that. This is nice that it's factored, because what this tells us, first of all, this 2 is on the inside of the parentheses. So anytime we're multiplying by some number times x, this is going to be a horizontal dilation. And because it's already factored, it's a horizontal dilation by 2. So, I'm sorry, a horizontal dilation, remember it's 1 over this number, so we have a horizontal dilation by 1 over the absolute value of this number, which is 2. So, horizontal dilation by 1/2, which means that our x-coordinates are going to be multiplied by a factor of 1/2, so in other words, they're going to be cut in half. So the x-coordinate of this point is -2, that's now going to be -1. The x-coordinate of this point is 1, it's now going to be 1/2. The x-coordinate of this point is 2, it's now going to be 1, getting a little cramped right there. And the x-coordinate of this point is 5, which is now going to be 2.5. So, our new function so far, g, is going to look like this. So we had a horizontal dilation by 1/2. But this plus 1, and again, this is why it's useful, because if it was written like this, it'd be tempting to say that it moves to the left 2, but that's not the case. We want it factored, because it's actually just moving to the left 1. And so if we move all of our points to the left 1, this one is going to end up right on top of this point. This one is going to end up right here. This one is going to end up right there. And this one is going to end up right there. So I know it's a little bit cramped to see, but our new function g is going to look like that. And so this is the transformations for number 6. Next, we want to look at these as algebraic transformations. So similar to the last assignment, we have that f of x is equal to 4x plus 3, and we want to figure out what g of x is. So first, this one I think is straightforward enough that we could just directly substitute 4x plus 3 for f of x. When we do that, we get 3 times 4x plus 3, and then plus 5. I'm putting our function in brackets just because some of these will have parentheses as well, and so I want to have a distinguishing grouping symbol. But 3 times, we're just going to distribute this 3. We have 3 times 4x plus 3, so that's going to give us 12x plus 9, and then we have plus 5. And when we simplify that, that gives us 12x plus 14. And so this is g of x in terms of f of x. For number 8, this is when it's going to get a little bit complicated. So what I'm going to do is first I'm going to figure out, or I guess I'm going to distribute this 1/2 with x plus 2. Let's see. So 1/2 times x is just going to be 1/2 x, and then 1/2 times 2 is going to be plus 1. So we want to figure out what f of 1/2 x plus 1 is. Well, that means that we have to replace x in this function f with all of this. That means that we have 2 times our new x is all of that, 1/2 x plus 1, and then we're going to add 6 to whatever that is. Multiplying that out, we have 2 times 1/2 x, which is just going to be x. And then we have 2 times 1, which is 2, and then plus 6, we get x plus 8. So now we know that all of this, which was, again, all of that, is the same thing as x plus 8. So g of x is equal to x plus 8 minus 1, which is going to simplify to x plus 7. And so this is our final answer for number 8. Okay, so let's continue to look at number 9 here. I've got to move my camera a little bit. But yeah, let's look at number 9. So we have the f of x is equal to 4x minus 5. We want to find g of x here. So what we can do is first let's just figure out what f of x plus 1 is. Well, f of x plus 1 is equal to, remember, we're just going to replace this x over here in f of x with x plus 1. This is equal to 4 times x plus 1 minus 5. Then we have 4 times x, and then 4 times 1. So that's going to give us 4x plus 4 minus 5. And this is equal to 4x minus 1. So now that we know that f of x plus 1 is really just equal to 4x minus 1, it may be easier to plug it into g of x now. So g of x is now equal to negative 2 times 4x minus 1, and then plus 5. And to be consistent, I mean, you can use parentheses, nothing wrong with that. To be consistent with the other ones that I've done, I'm going to put these in brackets. And then we have negative 2 times 4x, which is going to be negative 8x. And negative 2 times negative 1, which is going to make it positive 2. And then we have plus 5, and when we simplify that, that's going to be negative x, 8x, plus 7. And so that is our final answer. And for the last one, let's look at number 10, at least on this side. So we have to figure out g of x, and we have to figure out what f of 2x is. So again, to figure that out, I'm going to just do f of 2x. And so this function up here, we have to replace these two x's in particular with 2x. And when we do that, we have 2 times 2x squared minus 3 times 2x plus 1. So simplifying that, remember we have to square the 2 and we have to square the x. So when we square 2, we get 4, and then times 2 again, it's going to be 8. So this is 8x squared. Then we have negative 3 times 2x, which is negative 6x, and then we have the plus 1. So if we're trying to find g of x, remember, f of 2x is equal to all of this. So g of x is just equal to 8x squared minus 6x plus 1, and then plus 3. And so if we combine our like terms here, really we don't need the brackets, but it's equal to 8x squared minus 6x, and then 1 plus 3 is 4. And so that is our final answer for number 10. Let's look at the next side. So for number 11, we want to see what these numerical transformations are going to do. So we want to find g of 2 for number 11. So if we're already given this rule for g of x, all we really need to do is plug in 2. So g of 2 is going to be equal to f of 3 times 2 plus 1. So we just replaced x with 2. Now we have f of 3 times 2. Well, we have to multiply 3 times 2, and that gives us f of 6. And then we have to add 1. But now we can figure out what f of 6 is based off of this chart. X is 6, so f of 6 is going to be negative 2. So f of 6 is equal to negative 2 and plus 1. And then negative 2 plus 1 is equal to negative 1. And that's our final answer. Next, we want to find g of 1. So g of 1 is equal to 2 times f of 1 plus 2 minus 3. Similarly, we have to add 1 and 2 together. That gives us 2 times f of 3 minus 3. And now we can substitute, we can swap out f of 3 with whatever that's equal to. Well, when x is equal to 3, f is equal to 8. So this gives us 2 times 8 minus 3. So we have 16 minus 3, which is equal to 13. And that is our final answer for number 12. For number 13, we want to figure out what g of 2 is. So g of 2 is equal to 4 times f of negative x. So if x is 2, then we have f of negative 2. And now, we can swap out f of negative 2. There wasn't anything to simplify there. Well, negative 2 is 6. So this is going to be 4 times 6. And 4 times 6 is 24. And so that is our final answer. Next, let's look at the domain and range transformations. So we're given that our domain here is negative 6 and 8. And our range is negative 4 to 8. So we have to look at the transformations that are done here. First, we have this minus 3 out front. Remember, a number out in front of the function corresponds to a vertical dilation, and it's also going to be a vertical reflection. Both of those are going to affect our range. So we're going to multiply all of our values in our range effectively by negative 3. And if we do that, this comes out to positive 12, because negative 4 times negative 3 is positive 12. And then 8 times negative 3 is negative 24. For the 2x, remember, this would correspond to a horizontal dilation by 1 over the absolute value of this number, so by 1/2. So a horizontal dilation by 1/2 means that we're going to cut all of our values in our domain in half. So when we do that, we now have negative 3, 4. And so this is our new domain. However, our new range isn't quite right. Remember, this has to be from least to greatest. So we actually want to swap this out as negative 24, 12. And there we go. So now, this is our new domain and range for this function. For number 15, we have a domain of 0 to 5 and a range from negative 10 to 4. So for a domain from 0 to 5, let's look at our transformations. Well, the only values that are going to affect our domain here are just this minus 3 here. So remember, minus 3 means that we're going to move 3 to the right. And when we're moving to the right, we're moving in this direction. So we're going to add 3 to all the values in our domain. When we do that, we get 3, comma, 8. So domain got shifted right 3. And what about our range? Okay, well first we have to look at the vertical dilation here. So we have a vertical dilation by 2, and so we're going to multiply all of these values by 2. So we get negative 20, comma, 8. And then we have this other transformation over here, the plus 4. Remember, the plus 4 is going to move our function up 4. So this is another transformation on our range. And so adding 4 to everything in here to make this go from negative 16 to 12. And so this is our new domain, and this is our new range. For the last one, we have a domain from negative 2 to 4, and we have a range from negative 6 to 8. So a domain of negative 2 to 4, so the only thing that's going to affect our domain is this horizontal dilation. But remember, your horizontal dilation is by 1 over this number. Well, 1 over 1/2 is the same thing as 2. So we have a horizontal dilation by 2. That means we're going to stretch out all of our domain values by 2. So this is going to change this from negative 4 to 8. And the only transformation that we have done to our range is this plus 5. That's going to add 5 to all of our range values. So this gives us negative 1 to 13. And so this is our new domain and our new range. Let's look at number 17 now. So for number 17, we have, first of all, we have a graph of f here, but let's identify what all is happening here. First, we have a vertical dilation by 2. So let's just perform each of these transformations as they come. So a vertical dilation by 2 is, remember, going to stretch all of our y coordinates by a factor of 2. So this this point right here, negative 5 comma 2, is going to go to negative 5 comma 4. So the y value got stretched from 2 to 4. This point right here, we have a y value of 4. Now it's going to go all the way to 8. For this point right here, we have a y value of 2. It's going to go to 4. For this point right here, we have a y value of 1. It's going to go to 2. And a y value of 2. It's going to go to 4. So just the vertical dilation here already made our function look like this. So it got stretched out by a factor of 2. Now the minus 3 is going to move our function to the right 3, and then the minus 1 is going to move it down 1. So all of these points I'm going to do that. Right 3, down 1. So 1, 2, 3, down 1. 1, 2, 3, down 1. And I'm going to use a large dot to distinguish it from the old points. This point, 1, 2, 3, down 1. This point, 1, 2, 3, down 1. And this point, 1, 2, 3, down 1. And so now, our function, try to draw this as best as I can. going to look like this. So this is our new function. This is what g of x looks like. So that is done. Now we want to state the domain of g of x. So remember, if we project this function onto the x-axis, I don't want to get this too messy, but this point right here would come down right there, this point right here would come down right there, and every point in between would fill up all along the x-axis here. And so this function does include these endpoints. So our domain would be from -2 to +6. Now what about the range? Again, we're going to project this function instead of onto the x-axis, onto the y-axis. So this point would come over here, this point would go over here, this point would stay where it is because it's already on the y-axis. But if we squish our function against the y-axis, it's going to occupy all of this portion of the y-axis. And so we start with the smallest value first, so that's going to go from 1 to 7, and it does include both 1 and 7. So our new range is from 1 to 7. And now we want to find g of 2. So there's two ways that we can do this. We can do it the easy way or the hard way. First, let's go with the easy way. So g of -2, we just want to find, well, where x is equal to -2, what's the y value for this? We have a y value of 3, so 3. That was easy. Or we can use our function rule here, and similar to what we were doing in this section up here, we can use this rule to see that if we have g of -2, this is going to be equal to 2 times, oops, not like that, 2 times f of, trying to find, oh, -2, oops, sorry. 2 times f of -2 minus 3 minus 1. Now we have 2 times f of -5 minus 1. We can swap out f of -5 by looking at our original graph. So f of -5, we look at, well, where is, when x is equal to -5, what is the y value of f? That is +2. So this is equal to 2 times 2 minus 1. 2 times 2 is 4 minus 1, and we get 3. So clearly there's two different ways that we can do this. I prefer to just look at the new transformed function that we have for g to get g of -2. So the zeros of g of x are going to be all of the points that touch the x-axis. However, notice that this function exists entirely above the x-axis. So this doesn't have any zeros. However, the y-intercept is where it touches the y-axis. Well, it does touch the y-axis all the way up here. And so that's going to be at y equals 7, or you can write it as 0, comma, +7. Either one of those works, but I personally prefer this. However, I'm still not sure which one the AP exam will necessarily present, so that's why I would want you to know both of these. But if you write y equals 7 on a free response or something, that should be fine. So that concludes number 17. Now we just have the best part, the test prep. So test prep for 1.12b. So we have this function, and we want to find the transformation of the graph for y equals f of 2x. So remember, this number right here, this is going to be a horizontal dilation by 1 over whatever this number is. Fortunately, it's just a 2, so they were nice. And a horizontal dilation by 2, and that means that all of our points, all of our x values for our points are going to be cut in half. So this point right here, the quality of the image is not that great, but the x value right here is -3, so the new x value is going to be right there. The x value of this point right here is 1.5, so it's going to be about 0.75. The x value of this point is going to go right there, and this one is going to go right there. So our graph should look like that. And so, just looking at all of our graphs, the only one that even looks remotely like that is C. Okay, let's look at number 19. Table of values for the polynomial function for selected values of x. So the graph of g is constructed by applying three transformations of the graph in this order. So a horizontal dilation of 1/2. So we start with f and horizontal dilation. So remember, horizontal dilation by 1 over absolute value of b, whatever this number is. So if this is equal to 1/2, that means that b has to be equal to 2. That's a tricky one. So they're kind of tricky. So we have f of 2x. Then they do a vertical dilation of 4. So vertical dilation of 4. That one's nice because it's just a 4 out front. And then a vertical translation by 6 units. So when they do by 6 units, that's going to mean by +6. So they're not indicating up or down. However, if it was by -6 units, that would be down because it would be -6. But we now know that g of x is given by this. And so if we want to find the value of g of 4, well, g of 4 is equal to 4 times f of 2 times 4 plus 6. Well, 2 times 4 is 8, so really this is 4 times f of 8 plus 6. What is f of 8? F of 8 is -12. So this is 4 times -12 plus 6. 4 times -12 is -48 plus 6. And then -48 plus 6 is going to be -42. And so that gives us answer choice B. And for the last one, we have the function g is defined by f such that g of x is equal to 3 f of 2x minus b. Okay. So if f of 2 is equal to a, f of 4 is equal to 8, g of 1 is equal to 7, and g of 2 is equal to 19, what is the value of a? Oh, gross. Okay. I haven't even looked at the answer key, so we're just going to see if this is right. So we know that our information, and this is how you work this on an exam. You just kind of see what information you're given and see what you can kind of figure out about using the information that you're given. So we have 3 times f of 2x minus b. Okay. So we want to find the value of a. Okay, so this is probably important, is that f of 2 is equal to a. So if f of 2 is equal to a and g of 1 is equal to 7, check this out. G of 1 is equal to 3 times f of 2 times 1 minus b. So f of 2 times 1, that's just going to be f of 2 minus b. If we know that f of 2 is equal to a, then we have that g of 1 is equal to 3 times A minus B. And we can't really do much else with that. We have that g of 1 is equal to 3A minus B. But we're given that g of 1 is also equal to 7. So this is important. And similarly, we have that f of 4 is equal to 8. I'm going to erase this real quick because we don't need it. So just erased what I wrote there. Okay, but we're given that, let's see, we want to figure out g of 2. So g of 2 is going to be equal to, according to our rule here, 3 times f of 2 times 2 minus b. This is equal to 3 times f of 4 minus b, which is equal to, according to this information, f of 4 is equal to 8. So this is equal to 3 times 8 minus b, which is 24 minus b. And then, because we're trying to figure out what g of 2 is, we're given that g of 2 is equal to 19. So we have two important pieces of information here. We have that 24 minus b is equal to 19. So if we solve that, we can deduce that b has to be equal to 5. So if we know that b is equal to 5, then we can go back over here and we get that 3a minus 5 is equal to 7. And now solving this equation, we have 3a minus 5 is equal to 7. 3a must be equal to 12. And now if we divide by 3 on those sides, we get that a has to be equal to 4. And so the answer would have to be B. And I'm not entirely sure if that's correct yet. And after checking the solutions, yes, B is correct. So that concludes all of the practice for 12B. So remember, we have a quiz tomorrow. It will be over 12A, 12B, and 11B, since we decided to move that to tomorrow as well. So please let me know if there's anything else that I can help you with, and I will see you then. Thank you.